Hi everyone, this is Rose. I am taking over the lecture for Trine because Trine is home alone with 3 kids and I'm home alone with 1 cat. So, seems fair enough, right? Okay, so today we're going to be talking about quantitative genetics. And these are the 6 topics that we will be covering today. I have divided the 6 topics over 5 videos, and you can find the videos both in PowerPoint format on Blackboard and on YouTube. So this YouTube thing is new. Let me know if you like it, because I've heard some complaints about the size of the PowerPoint slides and that it's bothersome to save all of them onto your laptop. So the YouTube videos might be a solution. Let me know if you think it's a good idea or if you say, please, Rose, don't be bothered. And the first topic of today is Mendelian versus quantitative genetics. Now, in the beginning of the course, we have been handling Mendelian traits. And you see Mendel there in the corner, looking happy as always. And Mendel's traits were very simple traits. It was wrinkled versus not wrinkled, yellow versus green, and white versus violet, whatever. They were quite simple traits. However, in real life, traits are often much more complicated, like height in humans, for example. So quantitative traits, they can be categorized in different, based on different characteristics. So the first one, like human height, it's a continuous trait, meaning that we have a range. So for example, you can be very short, you can be very tall, but most people are around the middle. Then there are categorical traits. And categorical traits can, for example, be color, or the traits from Mendel are very typically categorical. And categorical traits are often defined by fewer genes than continuous traits. Then there's this third category called threshold traits. And threshold traits, they're quite similar to continuous traits. The only thing is that you have two statuses, you could say. You have, for example, in disease, you have sick versus healthy. And whether you are sick or healthy depends on the threshold. Now, we can take as an example diabetes. Diabetes, to be called a diabetic, you have to have specific blood values. And these blood values are very continuous. You have most people are around the average, but some people have higher values. And then they have decided that you have to be above a specific threshold in order to be called a diabetic. Threshold trait. So the important message that I would like you to take home from this is that most quantitative traits are polygenic. And that means that the trait is determined by many, many genes. And most of these genes will have a small effect on the genotype. Whereas in the beginning, when we were only handling Mendelian traits, they were often defined by just one gene. Are you yellow? Are you green? Just one gene. Whereas with height, 700 genes that determine your height. That's a massive difference. And then there is all these 700 genes. We still see those Mendelian classes for each of these genes. But an important thing with these quantitative traits is that the environment has a huge impact on the phenotype. For example, with height, we all know that nutrition has a huge impact on height. You can have all the greatest alleles to make you the tallest person in the world. But the moment I take your food away from you from a very early age, you're not going to be very tall. Or at least you're not going to be as tall as you could have been. So that's an important message. Many genes, but also huge environmental impact on the phenotype. Now in this slide you have there are two nice illustrative examples of continuous traits. And both examples are about pigmentation. So what we see in on the left, it's with 2 genes, on the right it's with 3 genes. Now let's focus on the one on the right. What we see is that there are 3 genes, an A, a B, and a C locus. And for all the genes, if you have the small letter, it gives you no pigmentation. And if you have the capital letter, it gives you pigmentation. Now, when you then look in the F2, you can see all these different classes of the amount of pigmentation that you have. So you can be purely white, like the individual on the far left, or you can be purely dark, like the individual on the far right. If you're purely dark, it means that you got 6 portions of color. If you're completely white, it means you got 6 portions of white. But you can very, very nicely see that the majority is in the middle. They have 3 white and 3 black. Now the next slide shows this very nicely as well. So what we see here on the right is kind of like a graphical image of the previous slide. On the top we have 1 gene followed by a scenario with 2 genes, and then 3 genes, 4 genes, 5 genes. And then if each gene has this small additive effect, like we saw in the previous slides, where each gene would have a portion of white or a portion of black. If all this adds up together, and if you introduce more and more and more and more and more genes, you will start to see some sort of bell shape, like this. And this is the origin of the normal distribution that we for example see in human height. In Western men, for example, we see an average of 1.79 meters. And what you then see is that because there are so many different genes that have an impact on this height, you'll see this beautiful distribution. And when you follow the rules of the normal distribution, which we will discuss a little bit later, you see that we have the average of 1.79 meters, and then 2.5% of the men will actually have a height smaller than 1.63 meters, and 2.5% will have a height taller than 1.95 meters. But 95% of the men will have a height between 1.63 meters and 1.95 meters. Now, the key message that I want you to take home from this part of the lecture is that, like discussed before, quantitative traits are often defined by many, many different genes, each with a small effect. Like in height or in pigmentation, you see that each of these small effects eventually contributes to the phenotypic variation that we see. And also that very often these effects are additive. So that means like in pigmentation, like each allele gives you a portion of pigmentation.